Hi, I'm Amanda Gross, and I am working this time on a video of algorithms. In particular, going to look today at linked lists and BSTs, which stand for binary search trees. It's a type of tree within an algorithm. So we'll just jump in and get started. My goal for this video on algorithms is to make it kid-friendly enough that children can understand it, because some of my grade school kids probably will come onto my website and they might have an interest. So I'm trying to make it as useful as possible while giving a clear, somewhat understanding of algorithms for myself and other peers that might be having trouble too. So algorithms are defined nouns, and it's a process or set of rules to be followed in calculations or other problem-solving operations, especially by a computer. So what that means is it's directions, and the computer is simply following that set of directions. There's directions in life all the time, like back in grade school, just how to line up correctly, how to wash your hands, all those little things are sets of directions. The computer is following a set of directions that the programmer has given to it, and that is the algorithm. Some people have discussed algorithms and the sets of directions kind of like working with a recipe, and that, like, if you follow the directions correctly in the recipe, results in, a good algorithm that can function as the programmer wants it to function. This does not quite help me though, because here I am. See, I'm a cook. If I ever cook, I'm notoriously known for my bad cooking among family and friends. So yeah, this is me cooking. And if I think of algorithms as a recipe, hopefully it won't be quite disastrous as this, but who knows, it might be. But we'll go ahead on and we'll take a look at the linked lists. I like to think of linked lists as like a train. So you would have the head of the train, you would have the tail of the train, or the linked list. So the head and the caboose. And we'll look at the actual definition in just a moment, but the way I perceive them, the linked list in particular, is a train with information called nodes within each space in the train. So like every window would have a node. The caboose with the two windows would have a node. Numbers, data, names of people, whatever you're trying to link in this list. And even the front would have a node. You'd have single linked list, or you could have doubly linked list to go and connect throughout the train. And then we will go and look at insertion and deletion within inside the nodes. If you're not sure what node you're going to be using yet, like what data, what fact, like I have my numbers, but I don't know what number I'm going to have in the blue train in the second window, then it will become null until it is filled with information. It always goes back to null. So the actual definition here that I looked up is computer science. A linked list is a linear collection of data elements whose order is not given by physical placement in memory. So I'm looking at it like the train. Instead, the element points to the next. It's a data structure consisting of a collection of nodes that together represent a sequence, and the nodes come together in this line like a train. So like here's the train cars without the wheels and the caboose and all that. But if you look the bottom, they have the head of the train is 3200. Followed by 15, 3600, and they're saying 15 is the content, the node of the train. The 3600 is the address, the pointer of the next node. So 3600 points to 3, and that tells it where to go to the next. So it's called pointers. So the points to the next stage of the train, or connects it, kind of like the train cars were connected. So it goes to 3, the 4000. 4000 goes to 17, 44,000. Goes to 90, and then we didn't have one in the end, so it points to null. I mean, it's gone like back to the beginning. It's gone starting back. Null usually equals 0. And if you take a look too in the linked list with the numbers, like we got 15 through 1790 on all the left-hand side. So those numbers don't quite matter as much as in some of the trees, which we're about to look at. But if you take a look at the right side there, they had 3,600, 4,000, 4,400. Some nodes, some linked lists rather, they're going to go up. Sometimes they will go down. But this is a good example of the data form, number form of a linked list. Then on the right, we have the names of people, and each train car is pointing to the next node, the next part of the train, the next data structure. So head train, tail of a train, head's the beginning, tail's the end, and each one points to a node of data. So in this one, like with the names themselves, the arrows, they're like the pointers. Although in code, it's a lot more confusing than just pointing with an arrow. But we'll go ahead and we'll take a look next at what a tree in an algorithm might look like. What's going on in my brain too when I think of algorithms. So one type of algorithm, we're going to go into trees, binary trees, and binary search trees. I wanted to use this one as an example of a tree, just a tree. I made it into Christmas tree just for fun. It's aesthetics. So for like the Christmas tree, I made it, if you noticed, it's very unbalanced. Now, this is a true story about me. One year when I was like really low, I was like 6 or 7, I was trying to unbalance the Christmas tree. And I really was. I was trying to put all the ornaments to the one side. I thought it would be funny if it would fall over. I didn't quite get away with this, you know. See, I have my hee-hee and my little devil horns there. So that's supposed to be me as a little child trying to, you know, unbalance this Christmas tree. And there on the right is my perfect, always organized, never disorganized mother that was very upset because, you know, wow, that just so unbalanced. But a tree that is not a binary search tree and not a binary tree, just a tree in an algorithm can be unbalanced. It's kind of what makes the difference between a tree, a binary tree, and a binary search tree is the tree itself can be unbalanced. It can also have different types of things. Children. So we're going to talk about that. Like the star of my tree is going to be the root. Technically, if you think about it with a tree, you'd flip the whole tree upside down. And then if we had an upside down Christmas tree, we can think of Germany. But we won't get into that. The star as the root of the tree, or the top of the tree, the head of the tree in a way, is going to carry the first set of numbers. And then the number's going to go down. In a non-balanced tree, so when we take a look at a binary tree, instead of just the tree, they will have 0 to 2 children, is how they call it, respectively. So if you can see, that's bright yellow star, points down to 3 children. This also represents the unbalanced of a tree because they can only have 0 to 2 children. Then if you look at that dark blue, so if all these had numbers in it, every bulb on this Christmas tree had a number inside it, that would kind of give you a better idea. But say the dark blue has a number inside it, and it goes down to 3 children again. Then they also call them, they don't really call it like brothers and sisters, but they'll have a left side or a left child and a right side and a right child. And I'll show you more of that here in a minute with like kind of like a family tree. But if you can see, as it continues on down, that light blue has 3 children. The yellow bulb after the light blue has 1 pink child. The hot pink kind of ball there has a 1 blue child. The pink ball leading down from the dark blue bulb has 2 children, a purple child and an orange child. So children, all within the structure. They call them siblings if they're all lined up together. So like the red, the blue, and the red, the dark blue, the light blue are all siblings of the parent node, the star. The star could also be considered a grandparent node And if you skipped the blue, the red, the light blue, and you headed down to the hot pink, the light blue, and the orange, those are considered the grandchildren. And we'll take a look more like that in an actual family tree so we can get the idea a little bit better. But big thing to remember trees is if they are not a binary search tree and they are not binary trees, they can be unbalanced like this lovely Christmas tree when I was, 6, 7 years old and, trying to unbalance the tree at home. So this is a better example of like a binary tree as opposed to just the tree. So at the top would be the grandparent, the node, that's the grandparent, the head node. And then the grandparent had 2 children. So they refer to them as children. They have a left child and a right child instead of a boy and a girl. It's always left child or right child. And then down from the left child, well, technically in this family tree, in this family binary tree, she had a girl and a boy. So left child, right child. Then down from the grandma again, the right child, that boy had another child, 1 child. A binary tree can have 0 to 2 children. So this would work for binary. This would be mostly balanced, almost completely, the only missing another child there at the bottom. But there's a grandparent, there are grandchildren, there are siblings, there's left child, right child, and different parts of the example. So this is probably a best example to visualize what a binary tree might look like. If you want to try to use a picture in your mind. Okay, so we're going to take a closer look at binary tree structure of a binary tree. So you have your numbers. You've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now, if you're taking a look at this too, the way they're set up, because this will tell us the difference between a binary tree, binary search tree. So for one, they don't like have any numbers that are almost out of order. It always has the 0 to 2 children. They have a left side, right side, and a lot of balance to this tree. So the next one, for the binary search tree, all the numbers and the placements of the numbers will matter more. And you have to go down the tree to figure out which one's the right child, which one's the left child, according to less than, greater than. The right side will be greater than the left side. The top nodes are less than the bottom nodes. So we'll take a look at that type of tree next. Finally, we have an actual binary search tree. So let's look what I was talking about with the numbers. So the head node, the top, the root of the tree, 8. Well, then you'd like take the look at your list, your numbers. So you had a 3 and a 10. Now, if it's less than, it goes left. If it's greater than, it goes to the right. So 3 is less than 8. Therefore, it's going to go to the left. 10, greater than 8. So it's going to head to the right. Then we might have had the 1. So we're going to travel down the tree. Look at the 8. It's less than. Take it to 3. Is it less than 3? Greater than 3. Less than 3. Goes all the way left side. And that's the node. Then we have the 6. Start at the top with it. 8, less than 8. Go to the 3. Greater than 3. So it hits to the right. It's under the 3 node, but it goes to the right because it's 6. Next one. We just did we already did 1, the 6. Now we're on the 14. You start at the top of the tree with 8. 14 is greater than 8. It's going to head right. 14 is greater than 10. It's going to head right again. So that's why the 14 is over there. Then if you look at just those numbers. So the 8 is the grandparent of 1, 6, and 14. 8 has children of 3 and 10. 3 has children, a left child, 1, a right child, 6. So this is how we kind of read the binary search tree. Now, let's take a look at the numbers. 4, 7, 13. We'll start with 4. Go back to the top. Go to 8. 4 is less than 8. Goes left. So we're looking at 3 now. 4 is greater than 3. Therefore, it heads to the right. look at the 6. It's less than 6. Therefore, 4 goes left. It makes a leaf on the left. The ending parts are the leaf nodes. So like 1 is a leaf. 3 is not a leaf. It can't be a leaf because it's not the end. 4 is a leaf of 6 and also the left child of 6. Let's head to 7. We're going to compare it. Look at 7 to the 8. It's less than 8. It goes left. 7 compared to 3. It's greater than. It goes the right. 7 compared to 6. Greater than. Goes the right. So that's why it ended up as a leaf of the right child of 6. Now we have 13 to deal with. We start at the top again. We look 13, 8. We compare it. 13 is greater than 8. Goes to the right. 13 is greater than 10. Goes to the right. 13 is less than 14, which is why it went to the left. So this is what a binary search tree does. And all the information comes together so that it can search, and a computer can do this in like seconds, where it took me, I don't know, 2 minutes, 3 minutes of video to explain all that and to go through this entire binary search tree in video form. Okay, I'm going to take a look at the actual code of the binary search tree and the actual code of the linked list next. Okay, so I did 2 different types of binary search trees that I'm working on. This is the first one that I turned in for a binary search tree. So I'll try to explain some of my code here. We have the files, the include files at the top. This is a node. I had a little trouble. I was looking at a video, and I'll just include it there in this video. Yeah, it's going to go away. It's under Udemy, and it was under the Mastering Data Structures and Algorithms using C and C++. So I was looking at this course and that professor to help me with this part of it. So I had a left child, a right child, so I'm calling my child here. L child is left child, R child is right child. Inserted the element. T was the root. We made 2 more nodes in 1 and 2, which becomes pointers R and P, so it points to the information. Data key, left child, point to right child. If it's null, it'll return pointer P. But while T is not equal null, pointer R will equal to pointer T. If the T heads to that data, it will turn with the left child. And then else if the T turns with the other data, it'll turn with the right child. So it's kind of like going down the tree, figuring out whether it's left, right, so on. Traverse and order is also heading down the tree. So in order, we're going to head first to left child, and then we're going to print the percent data that we're trying to find to head to the right child. This is where we're searching the BST. We enter the data, enter key, heading down to left and right child. Here is when we're inserting the node. So we've got the struct node P, int key, all of this to return pointer P, and our insert for that data. This gives me the height of my structure. Let's see. Oh, hadn't gone over that before, but there's predecessor and a successor. So predecessor is what comes before. Successor is what comes after. So if I wanted to say my root of my whole tree was 10, and below that we had numbers, I don't know, 5 and 15. I'm just trying to remember and making them easy so I can remember them as I talk about them. So 5 would be the predecessor, and 15 would be the successor of the children of that number 10. So what we would want to do if we got rid of the 10, either the predecessor or the successor would take the place. The way you find which one you want to take the place is the one that has the most amount of nodes, the one that has the most amount of children. So like in the family tree that I showed you with the grandma side, you'd want to head to the daughter's side. The predecessor side would have the most children. Therefore, that would be the side that you would pick. You can pick either, though. You could pick predecessor, you could pick successor, but you're trying to find the way that you can keep most of your data the same. So if you want to replace the root, then you're going to have to go down the tree, find predecessor, successor, pick one of them, whichever one has the most children. If they have the equal number of children, it doesn't matter. It's kind of your choice. But one of them will probably have more children than the other. That's the one you want to pick to become the new node. This is a delete function to delete the node, to delete one of the nodes. This is looking for the successor again. This one is giving my numbers value. So we were inserting 30, 20, 25, 10, 5, 20, 8, 30. Would be printf. Return element not found. And then this is the R search for the tree. Now, when I ran it, it really didn't do a whole lot of anything. And it comes up with errors again because I thought I corrected all the errors, but it keeps showing me errors that I did not type the name of the node, but I have typed the name of the node, and I've gone over this a lot, and it keeps coming back error, don't know the name of the node. So if you go to any of the nodes, like right here, this is where I named all my nodes. I struct node, node N1, node N2, R pointer, P pointer, T pointer. So I know it says compilation failed due to following errors. I don't know quite how to fix that yet. And I went to several professors yet, and yeah, didn't quite work ever. Now, this is the other one that I found. I got this one off of C Programming Tutorial Lessons 18. A professor showed me this site to try to get it. It's kind of doing the same thing, though, except this time, if you go to the red here on the right of the screen, all these red dots mean something's wrong. It doesn't like something. This time it doesn't like null, and I've tried to call null, and it, for whatever reason, does not like null, but it won't play until those errors are fixed. And even when I fix the other errors, and let's see, there we go. Run the last successful build. If you say no, they're still telling me that all of null is undefined, every single null, even though I have identified null. So I do not know what to do with this, but I'm going to leave it there, and I'm going to head into the video and leave that way, and hopefully I'll get some help correcting my binary search trees. I'm going to go ahead and add the video 2 for the link lists, because next up I need to change my link list anyway. So here we go. Going to head into link list next. Can do like elevator music while I'm waiting. All right, so here's my link lists. It's popping on. All right, and then a lot more comments in this code. This one did work all the way through, but here is your example of your linked list. And a lot more that I did a lot more with this, with the commenting. I did a little bit better with the linked list than I did. This is where I said to me building blocks, and I keep thinking train cars. Here's public, means that we can all see it throughout the rest of the class. Node, I'm calling the node the next node. Integer for the next set of data. This is under class node and public function, so the entire program can see it no matter where it is. And this one, this is the creation of the linked list itself. I gave it a length, gave it a node head, length node head, ability to make the data and display the data. We void insert, display, get length, data defined. Get length, we're going to return the length. The head is null until you figure out what numbers you want to place into your linked list. It's going to start with null, I'm sorry, excuse me. Down here we're adding 1 to the length. We're inserting the function, create linked list insert function up there. Okay. And if I go on down here, linked list display, so it's going to display to the screen when I run it. It's going to have integer to 1. It's supposed to read, if it works correctly, it only sometimes works correctly, to the console. This stands for console out, so it's going to head to the computer screen where the user can see it, the node value. And the node value is going to return the node value. It's going to say, hey, this is your node value that you are looking for. This is the data to find. So it's going to go to the head. It's going to have a function, data to find, it's trying to find that. When it finds it, it'll either say not found if it cannot find the data that I want it to find, or it'll say found it if they found the data I want it to find. We use this when I want to delete the node. There is one node. The list cannot be made empty comes up if it cannot delete the node. Once it deletes the node, it's going to free the memory here in this part for the free in, and for node, it's going to free that memory up again. If the node already exists in the linked list, it's going to say node isn't present in the linked list. All right, now down here, I was running it before, and I wanted to, because the data to find, I was trying to find number 25. Oh, here, it's going to pick a random number from 0 to 99, put a random number in. So it says insert RAND is rand for random. And you want to code it the exact same way. Some of these are codes that work for the C++. Some of it isn't exactly like completely C++, but like the programmers, other programmers go into your program, they're going to want it the same way, you know. Like it doesn't matter if you call it orange or banana or butterfly, but at the same time, I'm sure other programmers will get very annoyed with you if you, like name a random number butterfly instead of rand, R-A-N-D for random. That's going to irritate them. So you want to try to stick to what everybody else does for this one. Okay, but it's going to turn back the percent when it tries to find it. List display, it's going to display it to screen, get linked again, return 0 at the end. You always want to return 0 when you're coding. Well, not always, but if you want it to like help the program. So I'm going to go ahead and play. This one is building, but it doesn't really do much. It just does linked list line 188 because I was trying to find 25, and that's my breakpoint. So it is headed to the breakpoint at least. Let's see. And if I go to, I don't know, it somewhat works though. Let's see. What if I stop it and, oh wait, I know, that's right. What if I do this again? And then if I go into step into information, there we go. So it did find this part of the pointer. I don't think it found 25 though. And then if I tell it to step over just a little bit, there we go. Oh, hey, data to find 25. Maybe it did find 25. Cool, so it kind of did. Maybe. Data find 25. Oh, okay, so it took 1 millisecond maybe of elapsed time to find 25. It found 25 then. Oh, good. See, there we go. Linked list working. The BST does not work, but I think the linked list works. So I'm going to stop debugging, and I'm going to add this video into the PowerPoint, and I think I'll turn this in for my linked list plus my binary search trees. So I think that's it for this one. I will make a new video coming up soon for the sorting. Thank you and have a good day. Oh, it would help if I stopped the camera, huh? There we go.